Have you ever wondered where the idea of a logical proof even comes from? That step-by-step argument that proves something is just undeniably true? Well, it wasn't born in a philosophy class or a courtroom. It came from geometry. And today, we're going to dive into the work of the man who basically created the blueprint for how we think, Euclid. His work wasn't just about triangles and circles. It was about building a whole new way to find certainty.
So here's our game plan for this explainer. First, we'll take a look at what geometry was like before Euclid came along. Then, we'll break down his revolutionary system. After that, we'll get into the surprisingly tricky foundations, understand the rules of the game he set, and finally, watch it all come together to build a perfect, rock-solid proof.
Okay, before we can really appreciate logical proofs, we got to understand the world that came before them. We need to see what geometry was when it was just a practical, hands-on tool for getting things done. The name itself, geometry, tells you everything you need to know. It literally means earth measuring. For ancient civilizations, this wasn't some abstract class you took in school. No, it was a survival tool. Think about the ancient Egyptians. The Nile River would flood every single year and just wipe away all the property lines. They needed geometry to redraw those boundaries. It was all about solving real-world problems. And for thousands of years, people got really, really good at this practical geometry. You can see it in the incredible grid-like cities of the Indus Valley. You can see it in the mind-blowing pyramids of Egypt and in the super precise altars built in Vedic India. They knew what worked. But then the Greeks came along and started asking a brand new and kind of annoying question. Why? Why does it work? And this quote right here, it just hits the nail on the head. All that ancient knowledge was basically a collection of results. It was a list of facts and recipes. You do this, you get that. But there were no general rules, no proofs. They had results without the reasons. And that's the key difference, right? Knowing that something works versus knowing why it works. And that gap is exactly what Euclid was about to fill. So this whole problem of having results without reasons, this is where our hero steps onto the stage. Around 300 BCE, there was this math teacher in Alexandria, Egypt, named Euclid, and he decided he was going to fix this mess. And in doing so, he didn't just change geometry, he changed how we think about knowledge itself. Now, Euclid didn't invent all of this geometry from scratch. His real genius was that he was like an architect for ideas. He went around, gathered up all the known geometric principles of his time, and then he organized them into this single, breathtakingly logical structure in his book, Elements. He created a blueprint for knowledge. And this is his method. It's so elegant, so powerful. Just 3 steps. Step 1, define your most basic terms. Step 2, lay out your foundational assumptions. These are the things you just accept as true without needing a proof. And then step 3, use those definitions and assumptions to logically prove new, more complicated truths. Simple, right? But absolutely revolutionary. So let's see how this thing is built. Step 1 of Euclid's blueprint was definitions. But right away, he slammed into this really fascinating philosophical wall. How do you define the simplest, most basic ideas of all? He started with stuff that seems easy enough. A point, he said, is that which has no part. A line is breathless length. Okay, sounds good, but is it really that simple? Not really, because you immediately run into a problem. To define a point, you have to use the word part. Well, what's a part? To define a line, you use breadth and length. What are those? You see the issue? You get trapped in this endless chain of definitions, like a dictionary where every word is just defined by other words you don't know. So Euclid and the mathematicians who came after him made this incredibly profound choice. They decided that some ideas are just so fundamental, you can't actually define them. A point, a line, a plane, we just accept these as undefined terms. We all kind of know what they are intuitively, and this is a huge insight. Every system of logic, no matter how strict, has to start with a little leap of faith. Okay, so with these intuitive, undefined building blocks in place, Euclid needed some rules for how to put them together. These are his foundational assumptions, the absolute non-negotiable truths that are going to hold up his entire logical building. And he did something really clever here. He split his assumptions into 2 different types. On one side, you have the axioms, or common notions. Think of these as universal truths that apply to everything, not just geometry. And on the other side, you have the postulates.
These are the specific starting rules for the game of geometry itself, like the moves you're allowed to make on the board.
The axioms are basically just pure common sense. I mean, the whole is greater than the part. Yeah, no kidding. Nobody's going to argue with that. These are the kinds of self-evident truths that are the bedrock of all logical reasoning. The postulates, though, are a little different. They are the specific permissions for what you're allowed to do inside of geometry. They say, yep, you can draw a line between any 2 points. You can take a line segment and extend it forever. You can draw a circle, any size, anywhere you want. These rules set the stage for all the constructions to come.
All right, here we go. We've got the undefined terms. We've got the axioms. We've got the postulates. Now for the payoff. Let's put Euclid's blueprint into action and watch how he used this amazing system to build new, absolutely certain knowledge.
So let's take a crack at the very first proposition from his book, Elements. The challenge seems simple. Given any old line segment, can you prove that it's possible to construct a perfect equilateral triangle on top of it? And I don't mean just draw one that looks pretty good. I mean prove that it's perfect. Here's how he does it, and he only uses the rules we've already established. First, you take your line segment. Let's call it AB. Then, using postulate 3, you draw a circle with its center at point A, and its radius is the length of the line. Then you do the exact same thing, but you start at point B. The two circles are going to cross each other at a point up top. We'll call that point C. And this is where the logic just clicks beautifully into place. Okay, look at that first circle we drew, the one centered at A. Both the line AC and the line AB are radii of that same circle, so by definition, they have to be the same length. Now look at the second circle centered at B. BC and AB are both radii of that circle, so they have to be equal too.
So let's just lay it out. We've shown that line AC is equal to our original line AB. And we've shown that line BC is also equal to our original line, AB. So now we bring in axiom 1. Things which are equal to the same thing are equal to one another. And boom, it must be true. All three sides, AB, BC, and AC, have to be equal. We have just proven, with absolute logical certainty, that we have a perfect equilateral triangle.
And that was just the very first proof. Using this exact same rigorous method, Euclid went on to prove, get this, 465 different propositions, or theorems, in Elements. Each proof was built on top of the ones that came before it, creating this massive, unshakable fortress of logical certainty. You really can't overstate the impact of this. Elements became arguably the most influential textbook in all of history. For more than 2,000 years, it didn't just teach people geometry. It taught humanity how to reason, how to think logically, how to build these incredible, complex arguments from the simplest possible truths. So, here's the final thought I want to leave you with. Euclid created this amazing, perfect, logical world. But just remember, the whole thing rests on a handful of postulates and undefined terms that you just have to accept on faith. You can't prove them. So, if even the beautiful certainty of mathematics rests on a foundation of unproven assumptions, what does that say about everything else we think we know?